slide, I'm going to introduce mathematically the type of general problem that I'm going to deal with during this presentation. This general problem is a conditional stochastic program. The idea basically is that we want to find a decision X within a feasible set capital X, such that the expectation of a cost function F is minimized, and the key word here is minimized, given that some auxiliary information is available to the decision maker. And this auxiliary information is what you can see here as written as set equal to set 0. We take the expectation of the cost function because we assume it is affected, or we know it is affected by some uncertainty, which we represent with the random vector y. The auxiliary information, the side information that we are going to call the context, is modeled by another random vector set, which we believe may have some predictive power on the uncertainty y, and that has taken the value set equal to set 0. Q here is the joint distribution of set and y, while Q G tilde is the conditional distribution of y of the uncertainty given the context set equal to set 0. So we have two different ways of writing the same expectation. One in terms of the joint probability distribution of set and y, and one in terms of the conditional distribution of y given the context set equal to set 0. So this is an example of a conditional stochastic problem, a very silly example. Suppose that we are running an ice cream shop and that at 10 a.m. in the morning, we need to decide how much ice cream we are going to make for the afternoon. The amount of ice cream that we're going to make is our decision X. At 10 a.m., however, we don't know the demand for ice cream in the afternoon, but we can use maybe some available information, which again, we refer to as the context. For instance, the temperature at 10 a.m. in the morning to make a better decision, because we know that there might be a strong relationship between the morning temperature, our variable set, and the ice cream in the afternoon, our variable y. So the goal here is to exploit the relationship between the temperature at 10 a.m. and the demand for ice cream in the afternoon to make a better decision X, that is to know better how much ice cream we need to prepare. Okay, so we want to solve the conditional stochastic problem that we saw before in the first slide. However, we are faced with a fundamental challenge. Neither the true joint distribution, the Q, nor the conditional one, the Q G tilde, is known at the moment we need to make a decision. The only thing we have is a data sample that we write like set I hat, y I hat of size n, of the joint distribution between the context and the uncertainty affecting my conditional stochastic program. So what do we do against this challenge? Here you have some possible solutions approaches. This is just an introduction, a mathematical introduction of the approaches that we're going to see with examples later. Okay, all these approaches are based on building surrogate or approximate model for the conditional stochastic program that we really want to solve. The first one is the classical or traditional forecasting approach. The idea is that we use the data, which is the only thing we have, the data, to infer the expectation of y given set equal to set 0. Then we plug this expectation, which is a point estimate of my uncertainty, we plug this expectation in a minimization problem, and we pray for this surrogate minimization model, which is a deterministic one. This is no longer a stochastic because this is a point estimate. And we pray for this deterministic optimization problem to have a solution as close as possible to the one we really want to solve, of the conditional one. Solution as close as possible, we mean in terms of the decision variable and also in terms of the objective function. This approach is essentially wrong from the outset because it ignores the uncertainty and its impact on the cost function. Alternative, we can also try to learn a rule mapping the context set directly to the decision, to the optimal decision, in the hope that this mapping rule is also as close as possible to the solution to the original conditional stochastic program. One of the major problems with this approach that directly estimates the decision itself instead of the uncertainty is that it doesn't guarantee that the decision provided by the mapping rule be feasible, that is, be in the feasible set capital X. From this point on, I must admit that I think this approach has many disadvantages, so I'm forgetting about this possibility for the rest of the presentation. There is a third approach that is similar to the traditional one. The idea is to use the data to compute also a mapping rule from the context to the uncertainty. In this case, this is also the conditional expectation of Y given set is also a mapping rule that is traditionally known as the point forecast, as the conditional expectation, right? But the idea here is that we are going to fabricate a different mapping rule from the context to the uncertainty, which very possibly will be different from the conditional expectation that we saw before, such that, again, the resulting deterministic problem is indeed closer to the original one. The last approach that we're going to discuss in this presentation is totally different from the rest. It's a different philosophy and consists in using the data, the same data, to get a proxy, this proxy that we represent with the hat, of the conditional distribution of Y given set equal to set 0, in the hope that this approximate conditional stochastic program, because this is another conditional stochastic program, like the previous one here, which is deterministic. But this is a conditional stochastic program where the expectation is taken over that proxy that we have made for the true conditional distribution, which is unknown, the Q cheat tilde. Okay. In any case, the traditional forecast, the decision rule, the smart forecast, which I also call value-oriented forecasting, or the proxy of the conditional distribution, all of them must be inferred from a sample of the joint distribution of Z and Y from this sample. For convenience, in this presentation, I may also use Chi to denote the pair of random variables, the context and the uncertainty. All these approaches are theoretically discussed in these two papers of ours that have been recently published, in case that some of you would like to delve into this topic. Okay, but this presentation is about power system operations. So now I'm going to discuss an example taken from power system operations, where we're going to see what I mean by value-oriented forecasting, or smart predict then optimize. More specifically, in the example that I'm going to present just in the next slide, we are going to contrast the traditional forecasting approach, where we learn the relationship between the uncertainty Y and the context, ignoring the objective function, the cost function, and the feasibility set of my decision, okay, with the value-oriented forecasting approach, whereby we also learn the very same relationship, but taking into account the objective function and the feasible set X. I have called this first illustrative example contextual merit order dispatch under uncertainty. Suppose that we have a classical two-stage electricity market comprising a forward market followed by a real-time reoptimization phase. Our forward market is going to be very simple. It is just a merit order dispatch based on marginal production cost. So we have a set G of generating units whose forward dispatch is denoted by GJ, with marginal cost CJ and maximum capacity GJ max. This constraint here enforces the market equilibrium, that is, generation needs to meet demand. And L hat here represents a point estimate or forecast of the net system load. As I said before, the minimization of the production cost in this forward market leads to dispatching units from lowest to highest cost. This is going to be just an illustrative example. Then we have a real-time market that takes as input the forward dispatch, which we denote with GJ star, and where upward and downward regulation is deployed at marginal cost CJU and CGD to ensure the power balance that we have here between generation and demand during the real-time operation of the power system. This LB here is the realized system demand per node. B represent the set of nodes. In real time, we do enforce the transmission capacity limit of the set of lines L, where ML here represents or corresponds to the L row of the matrix of power transmission distribution, power transfer distribution factors. Finally, capital RU and capital RD are parameters representing the maximum reserve capacity provided by the units, both upward and downward.
A quick question.
Yes.
Why wouldn't you include transmission constraints in the forward market to make it more feasible for real time?
Yes, because as I will discuss later, the estimation model that I'm going to present next is going to be much more complicated. You can do it, but it's going to be much more complicated than if we remove those constraints. Okay, so it's just for simplicity. You will see now in the estimation model. Okay, so we make the very reasonable assumption, I think, that we have a data sample consisting, this data sample here, that consists of M pairs, Fi, Li hat, where Fi is the classical point prediction of the system-wise net load, and Li is the vector of nodal net demands that we have observed in the past. So we are going to use the classical point prediction as the context. The Fi, we are going to use it as the context. And of course, the vector of nodal net demands L as the uncertainties. And we are going to explore two options when it comes to manufacturing the point estimate that the forward market uses. The first option is what I describe as usual practice, and it's just to set the point estimate L hat to the point forecast of the aggregate net system load. That is the conventional approach, where we use the point prediction of the total load. The second option is what I have called forecast upcycling. That is, we are going to try to aggregate the point forecast F by means of a very simple linear map characterized by coefficients Q0 as the intercept and Q1 as the slope. So the question is, how do we estimate these Q0 and Q1?
Juan, we also have a question regarding the setting in your problem.
Yes.
So Ogun asks if the temporal granularity of the forward market and real-time markets are the same.
Yes, here we are. Yes, here we are considering, for example, hourly intervals. Okay, yeah. So, well, the idea then is to train the forecast upcycling rule, this forecast upcycling rule that I'm going to insert here, as you can see. And how are we going to do that? By replicating the operation of the two-stage market over the data set Fi, Li. Okay, and this problem here is actually replicating the two-stage operation of the forward and the real-time market. As I said before, we set the point estimate L hat to the linear map, and we consider that the coefficients Q0 and Q1 are optimization variables in this estimation problem. This is kind of a two-stage stochastic program that probably most of us are familiar with, where the classical scenarios are actually the data points indexed by I, by the subscript I, in the sample, okay? The objective function in this estimation problem is the empirical expected cost that includes the forward cost and the real-time cost. This set of constraints here that I have highlighted in blue replicate the real-time operation of the power system, the real-time market per data point Fi, Li. And this set of constraints here enforce the merit order dispatch that drives the forward market again per data point, the simple forward market that we have considered. For this purpose, we have to use a binary variable per data point I and per generator J to enforce that merit order. If we think of it, this constraint here, these constraints here are just the optimality conditions of this minimization problem that constitute the clearing of the forward market. So we have a mixed integral linear program that scales linearly with the number of data points. Answering your question, Vladimir, if we had included the transmission constraint in the forward market, this estimation would be humongous. Okay, so that's the main reason.
Maybe another question also inspired by this formulation, but would be the solution Q0 and Q1 equal to 0 trivial to this problem?
Is a feasible solution?
Yes.
I mean, you mean Q0 equal to 0 and Q1 equal to
0. Then your load in your system will be 0 and your objective function will be minimized.
Yeah,
to 0,
that's possible. That's probably a feasible solution, but it's not the optimal one, because if you clear the forward market with 0 load, all generators are going to be dispatched at 0, like if there is no demand.
Yeah.
And then in the real-time market, you are going to suffer a lot of losses.
Yeah. Okay.
You know, so if you set this equal to 0, then you are going to pay a lot for the deployed reserve in the forward market, because we have, you see here this LBI hat. This is the the actual demand observed in the sample. So you're gonna have to compensate for that demand with the regulation. Okay, so now let's see a toy example using a small, my intention with this presentation is for you to understand what I'm doing. So we are going to use toy examples all the time. This is a small 3-bus system, as you can see, that consists of 2 generators, G1 and G2, a load, and 2 lines, line 1, line 2, and a load placed at the bus 3. Generator 1 is very cheap to dispatch in the forward market, but is very inflexible. Because, why? Sorry, because it has very high regulation cost and a capacity of 60 megawatts. Generator 2 is very expensive to dispatch in relative terms compared to G1, but is very flexible because it has very competitive regulation cost. It also has a capacity of 150 megawatts. Both generators offer their entire capacity as reserve capacity. Now we consider the following very simple joint probability distribution of the point forecast F and the actual aggregate net system load. With probability, this is something that we don't know. This is something that we are just assuming because we need to do simulations, right, and to do the example. But in reality, we don't know this joint distribution. This is the distribution from where we take, from where the data sample comes from. So with probabilities,
we also have a clarification question. Can you repeat again the meaning of F in megawatts? What's the physical meaning?
This is the point forecast. This is the if you go to a forecaster and you ask the forecaster, please, can you predict the load for tomorrow, the system load for tomorrow at a certain time period? The forecaster is going to give you F, while L is the actual load that is realized in real time, because the prediction always has an error, right? Is it clear more or less? Yes, right?
So.
I guess so. Okay, so this joint distribution is telling us that with probability 0.5, the point forecast, the predicted load at this node is going to be 25 megawatts. But then the actual load realized in real time is going to follow a uniform distribution between 20 and 30 megawatts. And with the other 0.5 probability, the predicted load at this node is going to be 35 megawatts, and the actual load that is realized in real time is going to follow a uniform distribution between 30 and 40. Very importantly, you can see that the forecast is unbiased in the sense that these numbers here coincide with the conditional, with the average value of the uniform distributions. So what I'm assuming here is that the point prediction that we are getting from the forecaster is unbiased. It's really nice. This is a very nice property of the forecast. I don't know if I forgot to mention that the capacity of line 1 is limited to 30 megawatt, while the capacity of line 2, we are going to consider that is infinite. Okay, so in this table, I provide the improvement of upcycling the forecast, that is the improvement of this mapping rule here in terms of cost with respect to just using the forecast as L in the forward market. We can do the math because we can do the math by hand because this is a very simple example. And note that if the context, that is the point prediction of the load at the forward stage, is 25 megawatts, the upcycling rule is telling us that it is better to underestimate the system load in the forward market so that we can reduce the need for downward regulation from unit 1, which is very expensive. Okay, so there is actually a trade-off between dispatching G1 at the very low cost of 5 in the forward market, but having to regulate it down in real time at a very expensive cost of 20 euros per megawatt hour. So the idea here is that it is better to decrease the dispatch of generating unit 1 in the forward market so that we can face the real-time stage with a better deployment of regulation. This becomes even more evident in the second case. That is when the point prediction is 35 megawatts. Since the capacity of line 1 is limited to 30 megawatts, it makes no sense to dispatch unit G1 at 35 megawatts because we are going to have to down-regulate it in real time because of the limitation imposed by this line 1, right? And this is going to be very expensive. So, and we're going to have to down-regulate it to 30 with probability 1. That's why the upcycled forecast given by this linear mapping is telling us that it's much better to dispatch generating unit 1 in the forward market at 30 megawatts, which coincides with the capacity of line 1. Okay, as I said before, this is a very simple example that you can actually solve by hand. And I'm using this to illustrate what I mean by forecast upcycling. If you are more interested in this, you want to learn more about these topics with more realistic experiments and more realistic forecast upcycling rules, you can read this preprint, which is already available in archive. Okay. Okay. So now I'm going to go through the second part of this presentation, which is going to be about the second approach for conditional stochastic optimization that we saw before, in which we use a proxy of the distribution of Y given the context set, if you remember.
Juan, and just before you start, we have another question in the chat.
Yes.
We can actually see them all there. So Abhishek Sharma asks, are you approximating the probability distribution for just one realization of historical data, or did you use bootstrapping or something like that to generate multiple samples to approximate the distribution?
In this, you mean in the actual paper here in this small example, we are just drawing sample from this simple joint distribution, right? So this is the model that we don't know in reality. In reality, we don't know this model, but here we're just assuming that we know it just to make the numbers and to see what happens by simulation, right? So the idea is that in reality, there will be coming some samples from this joint distribution, and from these samples of this joint distribution of Fi, Li, we would run this estimation model to compute Q0 and Q1, and then we compute these coefficients. Once we have these coefficients, we have a new forecast point for the following day. With this new forecast point of the following day, we use the upcycling rule, we improve the forecast, we implement that forecast, and we get an improvement. That's how we're doing it. Okay. So
there is just another question, Huami. So Tong Huang asked, can you explain what Q0 and Q1 are about? So I think it's a question about the weights of your regression.
What do they mean?
Yes.
The Q0 and Q1. Q0 and Q1. Q0 is the intersect of a linear function that maps the forecast that we have of the system load, of the load placed at node 3, to a new value of the load, which we are going to use, which in reality we use here in the forward market. With that value, with that new value coming from this linear function, we insert that value here. We clear the forward market with that value, right? And then we dispatch our system. Then we have to evaluate that dispatch during the real-time operation of the power system. It can be a more economical dispatch or a less economical dispatch, depending on how smart you have been when setting the value L hat in this forward market. Is there any other question about, because I'm gonna go through a second approach, as I said. So yeah, everything okay?
Looks like we ran out of questions about this first part.
Okay. So the second part is going to be a little bit more complicated because this approach is a little bit more mathematically tiresome. But anyway, let's try it. So the idea of this second approach, if you recall, is that we are gonna get a proxy of the true conditional distribution of the y, of the uncertainty y, that is the one affecting my cost function, given the context set equal to set 0. In the example that I'm going to put in a minute, this will be the conditional conditional distribution of the wind power forecast error given the point prediction of the wind power. Okay, we will see. So the idea is to get an approximate conditional distribution and then solve a surrogate conditional stochastic program, which hopefully is more tractable and that has a solution that is going to be close to the one that we really want to solve with the true distribution. Okay, so the challenge here is, where are we going to get that proxy from? Well, again, all that we have is a joint data sample, set I hat, y I hat. So the proxy, it has to come from this data sample, one way or another. Probably the most straightforward way to go to fabricate somehow a conditional, to fabricate that proxy is to construct somehow a conditional empirical distribution from the joint empirical distribution given by the data sample. So we have our data sample that we represent in this figure with the blue points. These blue points make up a joint empirical distribution of my context and the uncertainty y. The idea here is to use a local method for conditional inference, such as the k nearest neighbors or the Nadaraya-Watson estimator, to construct a conditional empirical distribution that we are going to use in the surrogate model, right? Like we're going to use as a proxy of the true conditional one. Okay, so this is the idea. We use, for example, a KNN or the Nadaraya-Watson kernel regression. And from the joint data sample, for example, we take the k nearest neighbors. Here is an example, a more specific example, and where we are using the 2 nearest neighbors. So again, the blue points are the joint data sample. We take the 2 data points, which are these 2 that are closest to the context. This is the context, the value of set, right? And these 2 orange points or red points constitute this conditional empirical distribution that we use as a proxy in our conditional stochastic program. Okay, this is the resulting surrogate optimization model, which is also a conditional stochastic program, but over a conditional distribution whose support is given by 2 points, the 2 points provided by the 2 nearest neighbors. Okay, so that's the idea basically. By the way, this is actually what they propose in a recent paper by Bertsimas and Kalus. Okay, that is, I think, is published in Management Science. Of course, this is not going to work well. I can tell you that already, especially when we have a small sample size, because this surrogate model that you can see here, I mean, with more neighbors, is going to be very optimistic and will suffer from the curse of the optimizer. Essentially, this is going to happen because these 2 points cannot represent well enough the true conditional empirical distribution. For this reason, in another paper also by Bertsimas, McCord, and Sturt, they propose to minimize over the worst case conditional distribution within a Wasserstein ball of radius rho that is centered on the 2 points given by the 2 nearest neighbors that we had before. So the idea is that since we know that this distribution, this 2-point distribution, is going to be a very bad proxy of the real one, what we're going to do is to do a distributionally robust optimization approach where we protect our decision against all the distributions within a Wasserstein ball whose center is given by the 2 orange points. Okay, so for those of you who are not familiar with the Wasserstein distance, just to say that it's a probability metric to measure how different 2 distributions are, and that can be spread itself as a minimization problem, which is actually an optimal mass transportation problem. Okay, but in this case also, they are forgetting about something that is critical when doing conditional stochastic optimization. The conditional inference itself, the job done by our 2 nearest neighbors, that is the center of the Wasserstein ball, is also itself uncertain, that is ambiguous. Therefore, the Wasserstein ball proposed by Bertsimas can be totally misplaced in the space of Wasserstein balls, especially if the local inference method, if our 2 nearest neighbor is not doing a job good enough. Okay, and this is probably happening when the sample size is small. Okay, so what we propose instead is that any of the neighbors, any of the blue points in the figures can indeed contribute to the conditional inference. That is, any of these points can contribute to form the center of the Wasserstein ball. Of course, they can contribute within a certain transportation budget in such a way that the neighbors, for example, this one, that are farther away from the context, from our value of set, will consume more budget. This way, we can construct an ambiguity set that is especially tailored to conditional stochastic optimization, because it is protecting ourselves also against the ambiguity related to the conditional inference, to the local predictive method that we are using to construct the center of the ball. Okay, so this is how our ambiguity set looks mathematically. I'm not going to go through this definition. The only thing that I'm going to say here is that the essential idea is that the center of the Wasserstein ball in our ambiguity set is no longer a single distribution, but it's a whole collection of distribution that is given by what we call a trimming set of the joint empirical distribution. Actually, I have an extra slide in the end with an example of what a trimming set is, but I don't think I will have time to go through it right now. So if there is any one of you that at the end of the presentation would like to learn more about this stuff, just let me know. Okay, I do have this slide here, this illustration, to illustrate in an intuitive way what I mean. In our case, the Wasserstein ball can be centered at any possible distribution within this trimming set. Our ambiguity set is going to depend on 2 parameters, alpha and rho. Alpha somehow says the minimum amount of points here, the minimum amount of these blue points that must take part in the conditional inference, okay, in per unit, while rho is what we know as the transportation budget. Perhaps in a more intuitive way, alpha, which is called the trimming level, controls the shape of the ambiguity set, while rho controls its size. Okay, so this is the mathematical introduction, and now we're going to illustrate how this is used for power system operations. Specifically, I'm going to talk about the contextual optimal power flow problem. The key idea is that, again, we're going to exploit in this application the fact that the uncertain wind power forecast error is strongly dependent on the point forecast itself. That is something very similar to what we did in the previous example. As you can see here on this slide, the shape of the wind power forecast error at a specific wind plant is very dependent or changes drastically depending on the value of the point forecast itself. If the point forecast is very high, the shape is skewed in this manner. If the value of the forecast is low, then the skewness of the wind power forecast error distribution is totally the opposite, right? And this is the fact that we're going to exploit with this contextual optimization, contextual optimal power flow. Okay, so in the formulation of the OPF problem, we're going to make some assumptions. For simplicity, we will consider that the nodal loads are deterministic. That is, wind power is going to be the only source of uncertainty in our example. This is just for simplicity. But for tractability, we are going to use DC, or linear representation of the transmission network. Furthermore, we will model the generation cost as convex piecewise linear function. This is widely used. And as I said before, our goal is to exploit a forecast wind power output, which is our context, our variable set, to get better OPF solutions. The notation that I'm using for this problem is almost the same as the one I used for the previous one. We are going to have a set of transmission lines L, a set of buses B, a set of wind farms W, and a set of dispatchable generators G. For a given wind power farm, the actual power output of the plant will be given as the sum of the predicted power output, Fm, at plant M, and the associated forecast error, omega M. Capital omega is the system-wise, is the summation of the wind power forecast error system-wise, okay? Similarly, the power output of a generator G will be given as the sum of the power dispatch Gj that we saw also in the other example, plus the deployed reserves, which is a random variable, because it is contingent on the wind power forecast error omega. As is customary, we are going to assume an affine control policy whereby each generator contributes linearly to accommodate the system-wise wind power forecast error through the participation factor Bj. Okay, the power balance between generation and demand implies that the summation of those participation factors must be equal to 1, and that the generator's power dispatch plus the predicted wind power production must be equal to the system load. Finally, as before, power flows are computed by means of the power transfer distribution factors. As for the OPF constraints, we have the constraint determining the reserve capacity provision, RD and RU, the capacity limit of the generators, the scheduled dispatch plus the reserve capacity provided must be lower than equal to Gmax or Gmin, depending on if we are talking about upward reserve or downward reserve. Okay, and the transmission capacity limits. Regarding the OPF objective function, the aim is to minimize the random total generation cost here, plus the deterministic cost associated with the provision of the reserve capacity downward and upward. As I mentioned before, the generation cost of a conventional power plant is assumed to be given as a convex piecewise linear cost function with SJ pieces or blocks. Okay, so we are going to take, as I said before, the array of wind power forecast errors at the wind power plant, F1, Fm, as the context set, so as to leverage their linkage with the forecast error in identifying better OPF solutions, right? The relationship that we saw before. This is what we want to leverage. The fact that the wind power forecast has a lot to say about the error that I'm going to have later. Very importantly, in this regard, the support of the conditional distribution of the vector of wind power forecast errors omega changes with the point forecast themselves. It is actually given as the hypercube determined by the Cartesian product of the intervals with extremes, the minus the point prediction, and the capacity of the wind farm minus that prediction. Okay, the error cannot be lower than this, not greater than this. Okay, this is just because of the physics of the problem, the nature of the bounded nature of the wind power production at a wind farm. So now we can formulate our optimal power flow, where we are going to use joint chance constraints. Here, X is the vector of decision variables comprising the generator's dispatch, the participation factors, and the provision of reserve capacity, upward and downward. Capital X again constitute the set of deterministic constraints, such as the power balance equation and the generator's capacity limits. And finally, 1 minus epsilon is the desired reliability of the OPF solution that we want to get. Okay, this is a joint chance constraint. The problem is that both the expectation and in the objective function and the probability of the chance constraint are computed over the joint probability measure of the context, that is the wind power forecast, and the prediction errors given the wind power forecast. But neither this joint distribution, right, nor the conditional one is known. So the only info we have again is the joint sample set I hat, omega I hat, or forecast and forecast error. So we are going to use the distributionally robust approach I presented before to cope with this issue. Okay, so this is the distributionally robust joint chance constraint OPF model, where we use the ambiguity set based on probability trimmings to factor in the contextual information. And as it stands right now, both this objective function, this supremum, and this infimum here of the chance constraint are intractable. To regain tractability for the joint chance constraint system, we are going to use the popular CVaR conservative approximation. Essentially, we first rewrite the joint chance constraint system as this single chance constraint on the maximum of the uncertain OPF constraints. And then we notice that the supremum over our ambiguity set of the CVaR at level epsilon of that maximum implies the satisfaction of the original joint chance constraints. The idea here is that it can be proved that the CVaR constraint 4 can be reduced to a continuous linear program under our ambiguity set based on probability trimmings. So it is giving us a tractable conservative approximation of this original problem, right, that we are going to be able to solve. Okay, so as for the objective function, we also must notice that this objective function, this supremum, is intractable in the space of the omegas, that is in the space of the vector of wind power forecast errors. However, it can be rewritten as a sum of univariate linear functions in terms of the aggregate system-wise forecast error, capital omega. This rewriting allows for an exact reformulation of the inner supremum as a continuous linear program if we work instead in the space of the capital omega instead of working in the space of the small omegas. Okay, so let's see now some results that we can understand from a toy example. Again, we consider a small 3-bus system, this time consisting of 3 lines, 3 conventional generators, G1, G2, G3, 1 load at node 3 again, and a wind farm located at node 2. The capacity of the wind farm is 60 megawatts, and all the lines have the same capacity here of 100 megawatts. This table here shows the capacity of the three generators together with the reserve provision capacity cost, downward and upward. In this small example, before that, this other table collates the convex piecewise linear functions that model the generator's production cost. Here we have the slopes. We consider three pieces, and here we provide the slopes, and here the intercept of the different pieces, linear pieces. In this small example, and this is important, the contextual information is given by the fact that the point prediction, that we know that the point prediction of the power output of the wind farm here is equal to 30 megawatts. So the forecaster that we have working for us has predicted, for a certain time period, has predicted that the power production of this wind farm is going to be 30 megawatts. We are going to leverage the fact that this value here has a lot to say about the subsequent forecast error that we are going to suffer from. Okay, in this figure, we represent the unknown. This is again unknown to us, but we need to know it here for simulation. So we represent the unknown joint probability distribution of the pair point prediction, our context set, and the prediction error. This is the distribution from which we randomly draw, or nature randomly draws a number of n of those pairs, the pairs point prediction, prediction error. Notice, this is very important, how the support of the prediction error changes with the prediction itself, right? The support here is this one, the support here is this one. On the red line is this one. The red line corresponds to the context that we have, that we are considering, which is 30 megawatts. And the support is the red line of the conditional distribution. Okay. On the right, I represent the kernel density estimate of the true distribution of the error given the context. Okay, that is the distribution of the errors of the wind power forecast error conditional on the point prediction being equal to 30 megawatts. These are the methods that we are going to compare. DRR trim is what we propose. That is a distributionally robust optimization approach that exploits the context by means of our ambiguity set based on trimmings. That's why we call it DRR trim. KNDRO is the method that we explained before, that what was proposed by Bertsimas, McCord, and Sturt, that is based on a K nearest neighbor for the conditional inference. Recall that this method does not offer explicit protection against the ambiguous center of the Wasserstein bowl. Okay, and finally, we also have method DROW, which is a standard Wasserstein-based DRO that fully ignores the context. That is, this approach works with the marginal distribution of the wind power forecast error. Okay, I mean, it works with the marginal distribution that will result from projecting this joint distribution on the y-axis, from here to here. I don't have that illustration anyway. Okay, so here we consider a sample size of, here we consider a sample size of 30 joint data points, right? The size of our sample is going to be 30. We set the desired system reliability to 0.9, that is 1 minus epsilon is 0.9. This is the reliability of the OPF solution that we want to get. And we are going to compute the actual violation probability, okay, and the actual violation probability and the actual total expected cost of the OPF solution that is provided by each of the methods that I presented before as a function of the robustness parameter. In DRO trim, this robustness parameter is rho, okay, is the transportation budget. We perform 200 independent runs. That is, we repeat these computations over 200 different samples of size n equal to 30 each. That is, okay. And we then represent the average violation probability and the average expected cost. These are the lines The lines are the average. And also, we also represent their minimum and their maximum. And their minimum and their maximum are given by the shaded color. Okay, so this is, for example, the maximum violation probability over the 200 independent runs given by method KNDRO. Okay.
Juan, we have 5 minutes left from our
yes,
nominal
I'm
time,
about
so
to,
good be to wrap up.
I'm about to finish.
Thank you.
Okay, so 3 key messages here. All methods, if you see here, all methods need a budget greater than 0.1 to provide the desired solution reliability, which is this 0.1 here, right? This is the epsilon. Our methods always provide more reliable solutions that are significantly cheaper, as you see here, than those delivered by the KNDRO and the standard DRO approach. And 3, the solutions provided by our method dominate those of the KNDRO, both in terms of reliability. You see that our method is always below the other one, and in terms of cost, again, our method is always below than the black line. Okay, not only in terms of expectation, but also in terms of variability, as you can see. These plots are analogous to the previous one, except that they show the amount of total upward and downward reserve capacity procured under each method. On the one hand, DROW overestimate the amount of upward reserves, you can see it here, that are needed to ensure solution reliability. On the other, while it is true that KNDRO procure less upward reserve capacity, so it has a lower reserve provision capacity cost, then when it comes to the real-time operation of the power system, it has to pay a larger operational cost in the end. Okay. Now, this is the same as before, but with a large sample size, with n equal to 2000, that is with a lot of data and information. Again, here the actual violation probability and the actual expected cost, and that you can see that all solutions provide, all the methods provide reliable solutions for any value of the robustness parameters. However, the OPF solutions given by the standard DRO approach are around 2.3% more expensive than the other two. As for DRO3 and KNDRO, they become essentially the same because, as expected, the sample size is high, so the conditional inference is no longer uncertain. So both methods, let's say, that converge to be the same one. Okay. And the reason why DROW does it so badly is because, again, it provides much more upward reserve capacity than is needed. Okay, so if you want to know a little bit more about this topic, this is another preprint where you can delve into this problem. Just to conclude, a couple of remarks. If we are to predict some takeaway messages, if we are to predict the uncertain parameters of an optimization problem, that is, if we are to follow the classical scheme, data first, then prediction, then decision, there will be most likely a misalignment between the predictions and the decision loss functions. So my recommendation is forecast upcycling via contextual optimization. The challenge, as we saw, is tractability. If we are forced to predict, but we are allowed to apply instead a data decision approach without a predictive model involved, then exploiting the context in conditional and stochastic optimization implies to conduct a conditional inference, implies conditioning from a joint data sample. Okay, so my recommendation is to robustify the conditional inference too, and the problem, again, the challenge is tractability. I must say in this regard that our approach is nevertheless as tractable as the standard DRO approach that fully ignores the context. Okay, so that's all. Thank you very much for your attention. If there is any other question.
Yeah, thank you, Juan. We do have one question in the chat. Also, as you were speaking, we had a very hot discussion there, so thanks for that. Okay. And yeah, you can also feel free to unmute yourself, ask your questions directly. maybe while you're preparing, I will ask the question from Akoulas Stratigatos, who thanks for the presentation, and he has a question. Do you account for temporal spatial correlations of wind forecast errors in the set construction? It's about the second part of your talk, Juan.
If we account for spatial correlation?
Yes, temporal and spatial correlations of wind forecast.
Okay, a spatial, I mean, this may have several answers. We don't account for a spatial correlation within the ambiguity set. This is something that has been studied by other people like Adriano Arrigo, Yalarca Zempour, where they include a spatial correlation of the wind power forecast errors through copula bias within the ambiguity set. If you are referring to how we generate the data, we do include the spatial correlations, okay? But in the way we generate the data, but we don't construct an ambiguity set that knows something about the spatial correlation of the wind power forecast error.
And also the same question, the question from the same for Akoulas. Can the method deal with a large number of contextual information?
With a large number, it means a lot with a high dimensional set?
I suppose so, yes.
Yes, yes. It is true that there is a theoretical result that tell us that is the dimension of set, the context is very high, then the method suffers from the curse of dimensionality, because we need a lot of more data to make the conditional inference. This is something that happens to local predictive methods like the Natayara-Watson estimator and the KNN and all these methods that are based on distances, right? But in the simulation that we have done, we must say that we have never encountered this curse of dimensionality, and we believe, we conjecture that it is because the distributional robustness that we add protects against the curse of dimensionality in our case. But this is not a theoretical result that we have proved. It's just based on simulations.
Some more questions, please feel free to unmute yourself, ask your question directly.
Can I ask my question? This is Masud Baraki from University of Pittsburgh.
Yes, please go ahead.
Oh, sure. Thank you. Thank you so much for the great presentation and beautiful slides. So my question was that when you are going to define the L-hat functions, you have approximate that L-hat with the linear regression functions with the two coefficients Q0 and Q1. So as you said, that L is the real-time load profile, right? But and F, you said that F is a forecasted load. But you have been used the L-hat in the day-hat market. But
I mean, I think what in the forward market we use this L-hat, but this L-hat we compare two options. When this L-hat is given by the point prediction given by a forecaster that we have hired, or when L-hat is given by the forecast upgraded with a linear decision rule that I have trained.
Oh, you're saying that in the current state of the art, short-term load forecasting, it's based on the F, right?
Yes. Well, when I say I didn't say a state of the art. I say that the conventional, like what they do in the TSOs, they predict the load that they are going to have for the following day, and based on that prediction, they clear their day-ahead market, right? So that's what I refer that this is the usual practice. It's not that a state of the art. We have you could also use stochastic programming or any kind of optimization under uncertainty technique to solve this problem as well. So the idea that we have here is that if the TSO doesn't want to solve a stochastic programming, robust optimization, distribution in robust optimization, because this is very difficult to solve, what we're going to do is to provide the TSO with this rule, so that the TSO receives the forecast, then the forecast goes through this rule, and the L hat that the TSO implements in the forward market is the one given by this rule. So this approach is like a more, it's not like a qualitative step ahead for TSOs, because they are using a point estimate of the load for the following day, but it's an estimate that we have improved, that we have recycled from the point forecast given by the forecaster.
That makes sense. Thank you so much.
You're welcome.
Well, all right, I think we are good. So we answered all questions, and it was all very interesting. Thank you, Juan M, for a wonderful presentation. Yeah, and yeah, I think we can stop here.
Okay, thank you very much for everything. I mean, for inviting me again. See you around.
Yeah, thank you, Juan M. Thank you.
Bye.
Bye.